Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, I'm pleased to introduce our guest speakers for today, Andy Kuhn and Tom Miller, both from the University of New Hampshire, Department of Electrical and Computer Engineering. Andy is an associate professor whose research interest is on speech user interface design. He's also the PI for Project 54, which, if you haven't seen the press coverage for, is a command and control application in police cruisers that assists police officers. Tom is his principal collaborator. Tom is a professor, also in the same department. His research focus is on adaptive DSP and control. Without further ado, Andy.
Thank you, Tim. And thanks for the invitation. We're both thrilled to be here. I wanted to say that if you have any questions, please interrupt. It's going to be, I'm going to start the presentation and Tom Miller will take over, so it's sort of informal. So please do interrupt if you have any questions. Here's the outline. I'll give a brief introduction of the Project 54 system. I'm not going to spend too much time on this because I'd like to turn to the speech-related issues. So I'll talk about some speech interface testing work, which happened probably over the course of a couple of years ago or so. We have some exciting driving simulator studies that I'd like to talk about. And I'll conclude that part of the presentation, and I'll turn it over to Tom Miller to talk about some speech recognition engine training work that he's done. So Project 54, how many people have had a chance to sit in a police cruiser? Front, back, I'm not going to... Okay, so if you had a chance to sit in one of these things, you know that they're busy places. It's a lot of equipment, there are a lot of toys, and they all compete for the attention of the officer. And that's a problem. It's a distraction. The primary thing that you need to do in any vehicle is driving. So the problem that we saw was you have these devices, they're distracting you. Why not create a system that has a single user interface and in fact really a speech user interface so that you can keep your hands on the wheel and eyes on the road. So that's what we did, and here's just a quick slide of the integration. So on the bottom right you see a couple of hardware devices, and these would be things like your lights and siren and so forth, and they're controlled by what we call applications. So app 1, app 2, these would be COM objects that are within the Project 54 software. There is some core software that allows these applications to talk to each other, so your radar can tell your ticket writing application what the speed was and those sorts of things. And all of them have access through the core software to the speech recognizer and the text-to-speech engine, so that if you're an application developer, you don't have to worry about having to talk to SAPI. You just basically get text messages back and forth. So this is the basic hardware and software setup, and I'm going to leave it at this. I did want to show a picture of the system in the car. And I'll go grab my pointer while I'm talking about this. So what you see here is that we have a center console, which basically houses all of the electronics that's necessary for this system. That's where the PC is. It's an embedded PC and so forth. You also see a couple of things here. The original user interfaces that come with the in-car devices. So there's the control head for turning lights on and off. That's the police radio, and that's the radar. So if you are averse to using computers, or your computer crashes, you're not left without anything. And I think that's really nice. You have a GUI and a non-working pointer, and also a directional microphone and push-to-talk button. So you tell the engine when you're going to talk to it, and you have this directional microphone to filter out noises. I wanted to quickly say that the system's deployed in roughly 800 vehicles around the country, primarily in New Hampshire. So these numbers are for June of this year, and at this point we're roughly at about 660 cruisers deployed in the state of New Hampshire. So thank you very much. So it's a reasonably big deployment, and probably it's over 100 cruisers in other states as well. I wanted to show you this slide, the system usage slide, in terms of mobile data queries. So this would be the New Hampshire Department of Safety. This is the state police. They can run data queries from their cruisers to remote servers. And I just wanted to, while I'm not going to talk about this part of the project, I just wanted to show you that we're talking about roughly 20,000 queries a month. So the system is widely deployed, and I wanted to show you that it's also widely used by the people who actually have it. All right. So let me talk about this business of how well the speech user interface works. First of all, what we have for the speech user interface, you saw the press to talk button and the directional microphone. We also have a Microsoft speech recognizer and a Microsoft text-to-speech engine. And we use grammars, so their basic context-free grammars would tell people exactly what they have to say to improve recognition. Now, by the way, this actually should work for officers, right, because they presumably expect to be trained. It may not work very well for the general public, but in fact, in this particular application, we think it works well. We had 27 volunteers, and we collected just under 50,000 utterances in the field over about a period of a year and a half. And we were recording utterances whenever the press to talk button was pressed. And we got these results. So basically, the speech recognizer, the speech user interface worked properly 85% of the time, and unrecognized 4%, and misrecognized 11%. We took a look a little deeper and saw that what we'd call speech recognizer error was about 1/3 of the time, and what we'd call user error would be 2/3 of the time. So what do we mean by these speech recognizer errors and user errors? For example, we would classify something like this, a speech recognition error. Here's an utterance where the officer is trying to say, or is saying 032185.
032185.
But they also have a police radio, right? And so that comes on. So if you're listening to it, you might have figured it out, but it's probably not quite fair to have the engine understand this. But we nevertheless qualify this as a speech recognizer error. You might say, well, 85% sounds pretty low. In a sense, it is. However, what's nice is that in these particular situations, officers are not getting frustrated because they realize that, repeating it again,
032185,
right after the previous utterance works fine, right? So they understand that, okay, there was an interference. That's not fair. Let me try it again. And so we found that even though 85% isn't, something that you'd necessarily boast about, it actually isn't that bad because people are not getting frustrated since they understand a lot of the reasons that things don't work.
And do you give back feedback?
Yes.
Okay.
So you and that's a very good point. So the speech user interface tells you what it heard, or whether it might say unrecognized, but it will come back. So this sequence here, you get it back, so you understand that it didn't work. As far as user errors go, out of grammar utterances were primarily the problem. So there were utterances that were not in any grammar, and this was probably a lot of the times this was actually part of training. The utterances in another grammar, that was often the case. So there's this hierarchy that you have to go through to get to certain utterances, and you could argue that that's not user error, that's a design error, but we're not going to get into that. And there are things like the press to talk. So for example, this person was trying to say patrol screen, and it's patrol screen, right, or something. So that may not work very well. I wanted to share a couple of other things. So for example, here's a recording of several tries of a person who's trying to say patrol screen, which should have been a valid command in that grammar according to the rules we set up, but we forgot to put patrol screen in the grammar. So that was our problem.
Patrol screen.
So,
Patrol screen.
So he's trying.
Patrol screen. Patrol screen. Patrol screen. I don't want you to scroll down. Patrol screen. Patrol screen. Patrol screen. Patrol screen.
He was persistent.
Patrol screen. 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 Why will this not recognize patrol screen?
So that was our fault. but it's also good to see that people do try multiple things, and we've seen this on ride-alongs as well, where they play with the system and they experience it and do make it better. This was kind of fun too. This was while working.
Front antenna. Patrol screen. Radio controls.
So at least people are having fun with the system, right? So that's good.
The reason why the first case,
Yes.
it didn't recognize that is because the environment is okay, right?
Yeah, everything's fine. We didn't put this into the context tree. That was our fault. We tell people how to figure out what's in the grammar, and basically you look at the graphical user interface, and whatever you see on the button, you should be able to say. And there was a button that was called patrol screen, but we managed to forget to put that into the grammar. Anyway, one of the newer things that we're looking at is our driving simulator study. So about a year ago now, we purchased a driving simulator from a Utah company, actually. And here's a picture of it. So what you have is 3 screens. So it's 3 channels in the front. There are the little projectors. There are also 2 extra channels. The 2 side view mirrors and the rear view mirror add up to 2 more channels, which is kind of a nifty setup, by the way. If you've seen driving simulators, oftentimes they'll have an extra screen in the back, which then you literally look at through a mirror. But this is actually nice because they have these side view mirrors that just have LCD screens in them. So that's how you end up with the side view and the rear view mirror. And then what we end up doing here is you'll see a better picture of this, but there's a little police radio in here that we're testing, and in essence we connect it to something like, for example, the Project54 system on a PC, and we're looking at, well, how do you interact and drive, and these sorts of questions. And in fact, that the 2 main thrusts for the driving simulator studies would be this business of what we call multi-threaded dialogues, and I'll talk about that in a second. And then how does the other thing is, how does the speech user interface in the Project54 system interact with your ability to drive, and how does it affect your ability to drive? Well, first, this multi-threaded dialogues business. This is a project that's a collaboration between Oregon Health and Science University, ourselves, and the University of Michigan Transportation Research Institute. And we're looking at how do you interact with multiple real-time devices through speech. So the analogy would be, if I'm driving and I'm talking to someone about, the upcoming talk tomorrow, and then someone is in the back and giving me directions, and every now and then interrupts me and says, okay, you need to take a right here, and I talk to that person about that, and then I go back to the original conversation, how do you best do this? And what we wanted to really look at is you have this manual visual task. So what is the manual visual task? Of course, there are multiple manual visual tasks in the world, but we thought that driving, in fact, is a nice proxy to probably a lot of them. And it's easy to find competent subjects, right? So you could also be doing this for extravehicular activity in space, but then the only competent subjects are astronauts, and that's tough to get. However, everybody pretty much drives. So if you wanted to have a nice task a nice manual visual task, we thought driving would be that task. The idea that we have for this multi-threaded dialogues is to observe how humans perform these multi-threaded dialogues, and how do they switch and keep track of context and so forth. And then try to teach the speech user interface to use this, these approaches, although we realize that the speech user interface and the humans have different capabilities, so we might be able to take advantage of different things within the speech user interface as opposed to what humans can do. So what we're looking at is human-human studies right now, in fact, and in fact that's what we're looking at right now at UNH, and I'll show you a video of that real quick, and also human-computer studies, which we sort of started out by at first, but then realized that we sort of went a little too far probably, and that the human-human studies would be the first thing to do with our driving simulator. So here's a video that I wanted to show you of the human-human studies. What you'll see here is a couple of people talking about trying to get, so basically a person driving and a person acting as a dispatcher trying to guide this person driving to a particular point. But as the maps project, I believe was called, the dispatcher has the wrong map. So that while the person is driving, they see the reality, and the person who's dispatching sees a map, but the map doesn't match the reality. And the purpose is really not to get from point A to point B, but rather to have them talk. Because otherwise, if you just have the right map, then you'll say, well, take a right, and then the person takes a right and they get there. However, if they can't get there because there is no right, then now all of a sudden there is a conversation going on. And at this point, what we're playing with is this part of the dialogue. And what's going to come in next is some sort of an interruption. And our current plan is to have some sort of an engine problem message that you have to talk to the dispatcher about, otherwise your car stops. So that you're actually, as a driver, you're being pushed to interrupt the current ongoing interaction by talking to the dispatcher. At any rate, here's the video.
You should have a RCO on the side.
So here's our driver.
Well, actually, I'm at the bank.
At the bank.
Yes, I see bank on my right.
On your right.
It looks like the place. Yeah, it looks like it's a place where I started from. I haven't the intersection. I go only left or right or back.
Left or right or back? Take a left. You should be seeing a stadium on your right.
So just a quick taste for interactions, right? So the person's seeing reality. He's being told to take. There's no way I can do that. And you see the map. It just doesn't match reality. And you see that there are actually the conversation is going back and forth. And now on top of this, of course, if you want to have multi-threaded dialogue, there should be another one, and that's coming next. Another area of work is this business of, well, how does the speech user interface and driving work together? And this is the setup in the simulator. So we have our directional microphone, and we have the push-to-talk button set up so you can talk to the Project54 system. And then we also have an actual police radio here. And so you can change channels on police radios. So police radios are sort of like your in-car FM, AM, FM radio, except for your AM, FM radio usually has 6 buttons for your preferences, right? Those are usually the channels you listen to. Maybe it has a seek button or those sorts of things. Whereas the police radio, for example, in the case of the New Hampshire State Police, has 200 channels that they have programmed in. And these 200 channels are grouped into zones because, you know, the manufacturer of the radio realized that you can't go through all 200 to get from one to the other. So in essence, if you want to go from channel 1 to channel 2, you pretty much need to know which zones they're in, which is okay because there's some sort of logic obvious as to how they're organized. But there are basically 4 buttons, so 2 buttons for zone up and zone down, and 2 buttons for channel up, channel down that you need to interact with. And on top of that, this is the little LED screen that tells you which channel you're on. So if that's truly what you're using, then you're pushing 4 tiny buttons and looking at a tiny little display. And the other question is, where are you actually going to place the radio? And I would contend that this is the best possible place you could really put it in the cruiser, because where else would you put it? I mean, you could put it where your actual radio would be, but that's further away and further down. You can't really put it up here. That just doesn't, you can't reach there, right? So I think that we pretty much put it in the best possible place. Nevertheless, it's not very convenient. You have to look away from the road, and you have to have your hands off the wheel as well. So this is the experimental setup, and basically what we ran so far is we looked at 2 experiments with 9 and 8 subjects, a baseline driving part where you drive and you're not actually doing much, and you just pretty much drive in a circle. And then after that, you start using the radio. And what I mean by using the radio, someone tells you, okay, change the channel to Portsmouth, New Hampshire, change the channel to Lebanon, New Hampshire. And then you end up pushing the buttons and kind of getting the feedback from the user interface of the radio box. And eventually you get to the radio channel. And this takes several button presses, both channel up, channel down, and zone up, zone down. And then you have a similar setup that uses the Project54 system speech user interface, where first you drive and don't interact with the radio, and then you just say, change the channel to Portsmouth, which is basically what you can do with the speech user interface. And we recorded the lane position, velocity, and steering wheel angle of the car, the simulated car. So here's a video of what's going on, and you'll see a person driving. There's the radio. He reaches over. Notice that he's looking away. There are the 4 buttons, so zone up, zone down. Here's another view. Take a look at the eyes and then the hand. And you can sort of see a little bit of what's going on with the road too, but it doesn't look that great, right? It's really a little iffy as to whether we should be doing this or not. And here's the data that we've collected over these experiments. So here's lane position in the case that you start driving, do not interact with the radio, and then these red lines show you where button presses occur. And you see that, in fact, there are quite a few. This is multiple button presses. You see that that's a little wider than this line here. So that's how many button presses it takes for you to change the channel. And you see that lane position is relatively steady and gets a lot worse. And this is one example for one of the multiple subjects, of course, and I'll show you the overall picture too. And then compare that to what happens with lane position when you use the speech user interface. So these would be the same exact changes in the radio channels. Of course, they're accomplished without button presses, but with one press at the press the talk button and then issuing the command of change the channel to the appropriate line.
This will assume that there's no error in the volume target.
That's true.
If there's error, what's going to happen?
That's a good question. But my guess is that what's going to happen is you're going to end up with an extra line, right, of having to do this again. Because what happens is you say, you know, Portsmouth, and it says Dover. Well, then you do Portsmouth again. So it'll be delayed, but I don't think that the actual driving performance would deteriorate.
Just to confirm, all police cruisers are equipped currently with this sort of radio changer?
That's true.
And they're using this in order to, what information are they getting out of it, and what's
Sure.
the sort of cognitive load of sort of understanding that information?
So that's a good question. And first of all, in New Hampshire, in fact, the little box that you saw is standard. And in fact, it's a Motorola radio, and it's quite, widely used. Something similar is used pretty much in every police cruiser, whether it's a Motorola box or a Kenwood or something else. And they all have the same idea. You have a lot of channels. They have to be organized in some sort of groups. You might switch between groups and then within groups. So I think that the cognitive load part that we're looking at right now is that, as opposed to why exactly you do this in the first place. And why you do this would be things like telling people where you are and asking them for information about, for example, a driver's license or a plate number. So you might be driving behind someone who drives erratically and say, could you give me the information on plate number 12345? However, that's not what we're talking about here. What we're talking about here is just the actual getting onto the appropriate channel. So in the case of a state police officer, you might drive around and get into the town of Durham, and now you need to talk to the police in Durham. And so what exactly does that mean? Well, you need to get on their radio channel.
The other question I have is, so you're showing lane position. What about, did you do any eye tracking?
We did not do eye tracking, and that's a good point. You can, in fact, either buy an eye tracker or build one yourself, and we did not do that. Velocity is something we also looked at. So people were told that they're supposed to be driving at a particular velocity. They would be following a car, for example, and a car would be going at 55 miles an hour. So follow this car, therefore, this is roughly 55 miles an hour or 60 miles an hour. And then you see that once they start playing with the radio, they do a lot more in terms of speeding up and slowing down, as opposed to when they do the speech user interface, where their variations are about the same whether they use the speech user interface or not. I thought that this was very exciting to see the steering wheel angle. So, of course, they do not steer off the road, but staying on the road takes them a lot more back and forth with the steering wheel when they are. So this would be driving without doing anything other than driving. And then when you start using the buttons, you see that how much basically they're doing this.
So you're comparing, are these different sets of users or the same users doing different things?
So there was 8 and 9 subjects, and a lot of them actually overlap, but there were separate tests. So this would be 1 week you do
Like
one.
the average of the
This is actually, these are not averages, and this is actually one example, but I'll give you the averages in a second.
So it is a within subject experiment.
That's correct.
Do you have a feel for this variation? Is it caused because they took one hand off the wheel, or just because they're in general distracted?
I think it's a combination. And one thing that we haven't done is, you know, if you remember, they actually have to use their left hand and then play with the. What I'd like to do next is to just see how well do you do with left hand only, whether you play with the radio or not. I mean, again, I think my guess is that all of our subjects were right-handed. So, if a left-handed person drives, this may not happen.
So, do you have any data on the total amount of time that it took to complete the changing tasks?
I don't, but that's a good question, and that should probably be done separately anyway to start with. There's a nice University of Michigan Transportation Research Institute. They came up with this rule of thumb that if it takes you more than 15 seconds to do while you're parked, you probably shouldn't do it while you're driving. And this doesn't actually take you more than 15 seconds to do. I mean, it certainly doesn't take 15 seconds to change from one channel to another, assuming you know, even if you don't know what you're doing. I actually do not know necessarily the zones, but it shouldn't take you more than that. So according to their little guidelines, it should be okay to do, but still. Yes?
Sort of unrelated, but so now like a lot of the higher-end cars have all the radio controls and CD built into the wheel.
Yeah.
Is there any thought of, it's sort of not helpful speech part, but in general, you're taking these radio controls and just putting them on the steering wheel?
They must be doing some of those tests that I know Humphrey is involved with, working with manufacturers, but they don't necessarily share that data. So that's a good question, yeah.
How realistic is the spacing of them having to change the channel? I mean, I would assume they would, change the channel maybe once every
that's
so
true.
often, and so
you're absolutely right.
It seems to me that it would be interesting to know whether it gets just worse, if you have to do a lot of these things in a row versus having some time to kind of settle down again before you do the next one.
I'm positive. You're absolutely right. It's not realistic in the sense that you will not keep changing channels 15 times over. You'll change to one. But also, people will not jump out or brake in front of you all the time. They will just do it once, and that's where the problem will happen. And it's probably, anyway.
Actually, turning on and off radios, and they seem to have pretty low cognitive load, whereas doing navigation has much higher cognitive load. So
you're right.
I wonder whether you have this kind of data to test on, Garmin kind of navigation system, just to see how much wider range there is.
Yeah, and that's, this is sort of we figured this is a low-hanging fruit because it seems like it's such an obviously not good thing to do, and it's so simple to test. But one of our newer thing that we integrated into the system is in fact mapping, and so we'll see how that. We'll have to set up some tests, but not necessarily with. You're right. I mean, you could. We just run to the card and we have a little device, and it seems to me that it's actually nice to have a passenger look at that instead of you having to look at it.
I might say, but again, the radio changing task is one. It's like if your cell phone, if you have 256 contacts on your cell phone, and you had to, while you're driving, pick one of those out to dial, but your cell phone's mounted down here. You can't even lift it up here and look at it. You have to look at it down here and go through that menu and find somebody out of 256. You're being distracted.
By the way, these are about. I think these are about. I think they're about 15 seconds apart. So it wasn't. It wasn't like, okay, do this now, do this. So we're supposed to get to the result and then drive and then do something again, which is a little difficult to see here because of the compressed timeline.
It just somewhat on the various slides seemed like the first initial spike is not nearly as high as the ones that are kind of subsequent, and so I was kind of trying to get a sense for whether the large spikes are representative of what you would get.
There's definitely the learning issue too, but I did drive around with officers who used PC to find out some, and they do this. Even though they do this all the time. So basically, they're not really learning. It's hard to learn not to.
I mean, I don't doubt it's distracting.
Right. And anyway, to compare, steering wheel angle stays very, very stable. Now here's the here's this data in terms of lane position variance, and these box plots which show the minimum, the 25 percentile, the median, 75, and maximum with some outliers as well. And over all of the subjects in the radio would be using the radio interface and using the speech user interface. You can see that lane position variance is certainly lower, velocity as well, and then steering wheel angle, truly big difference. So let me just say a couple words in conclusion before I hand over to Tom Miller. As of this month, we have roughly 800 cruisers with this system on the road, mostly in New Hampshire, but also in Massachusetts, California, and Maryland. And we do have a lot of industry participation, not in terms of people who do this for a living, where they put things into cars. I think are realizing that it's both good to integrate them for safety reasons as well as just synergy reasons for talking between multiple devices. I don't really have time to talk about other things that are going on, but I wanted to mention that we're looking at speech on handhelds and hoping to deploy this particular symbol device with a 2D barcode reader. If you look at your driver's license, my guess is that in Washington State you also have 2D barcodes on the back, so that if the idea is you don't have to type in someone's name or dictate someone's name, it's a lot easier to just scan this. We're looking in general, this is kind of a generic thing, of course we're going to try to improve it, but we're looking at different heuristics. So learning, for example, from all the data that we're collecting. There's another data collection ongoing right now, and seeing how we can actually improve the speech user interface. Intelligent interaction, so basically this multi-threaded dialogues, that's probably what that would be mostly aimed at. And then in fact there is quite a lot of non-speech work that's going on in terms of communication, and then yes.
What engine are you using on the Windows Mobile device?
I think isn't it also the 5.0, 5.1? No.
It's the one that ships with
the regular
the command and control app.
Oh, it's Yakima. It's the same one that ships with voice command?
Yeah, it's the one that ships with voice command, right.
Yeah.
Do you have any sort of operator assistance, so like a human in back of all this in real time to assist people, or
no?
What's sort of what do they do if it doesn't work? Like when the guy was repeating that screen over and over.
Each police department that is involved should have basically people who are trained, and then that's the person you go to. But it is a little bit. You're right. It's a difficult thing to set up properly for us as a university. The biggest deployment is in the state police, and in essence they pretty much come to us. We have a garage with a technician and another person there, and our engineers are often there. So in essence they'll show up and say, this doesn't work.
So there's no real-time support?
There's definitely no real-time support from us, no. No.
Have you done any kind of evaluation of high-stress situations? Like, I don't know if police officers, when they're in, say, a high-speed chase, will be using these same interfaces and stuff, because that actually changes everything.
Yes.
Right? Heart rate goes up, everything.
Right. Yeah, with tunnel vision, we haven't, no. And
the speech gets hyper-articulated.
One of the things that that might give us a better answer to that question is a more, our data collection so far has been, let's collect speech. And in fact, we're working on let's collect everything that's going on in the car right now. So we should be able to have a better picture of what exactly is happening in the cruiser, as opposed to just getting speech commands. So we're going to, first of all, collect graphical user interface messages, as well as messages that go on between individual devices. And we're tying into the OBD2, which is the in-car bus that, for example, provides speed information. So we ought to be able to tell, were the lights on, was the person driving really fast. So to a certain extent, we should be able to tell, what kind of situation this was at. But you're right, we haven't actually done that so far. Yes.
So when you try this handheld device, are you planning to use the in-car?
No. The idea would be to use it out of the car. And, honestly, I'm not sure how exactly it's going to be used. That's part of the pilot deployment. Yeah. But some things that we hear might be useful is, stepping out of the car to control the radar and finding better ways to pull people over.
Another thing is when you do this 400-second driving with the steering angle, I believe it's a straight, right? The emulation is a straight.
I think it was mostly straight, yes.
Straight line.
Yes, that's right.
I think if you do, turn, then the result will be more in favor of speech application, because with one hand turning, you will have more errors.
You're absolutely right. Yeah, the setting up of the actual simulation scenario is a big issue. You're right. And this isn't even, we're talking about, it will be interesting to see the leading car brake, or, pedestrians jumping out at inconvenient moments.
Right.
I'd like to say that as far as funding goes, it's the U.S. Department of Justice and NSF and the website, and at this point I'll hand it over to Tom Miller.
Pardon my old eyes. So I'm going to talk some about how we basically use the Microsoft speech recognizers in our Project54 application. And it may seem somewhat presumptuous from someone from New Hampshire to come to Redmond to tell people how to use Microsoft speech recognizers. But I thought, given our kind of unique application in the speech environment, and we have hundreds of cars out there on the roads over a number of years, you might be interested in what our experiences have been in using those engines, and we would be extremely interested in any feedback you have as to how we can do a better job. Our interest obviously is in high quality speech recognition. So the motivation for the kind of study I'm going to show you today was based on these kind of observations. One is that the 5.1 recognizer that we were using basically worked well right out of the box in our application in a speaker-independent environment for police officers, but not perfectly. And it seemed like training things you did in the lab with the background adaptation turned on and just using it in the lab seemed to make it work better. On the other hand, we had times when, by accident, the background adaptation got turned on inside a car, and generally speaking, those cars would show up later with a extremely poorly functioning recognizer. It would recognize hardly anything. And the only way to get it back to working was to reset the profile. I mean, to delete the existing profile and reset it and turn off adaptation. So we felt like there was a need to better understand that process and what was going on. Could we use it to our benefit, and were we doing something wrong? And then finally, there were things like thresholds, recognition threshold, and that kind of thing that were available and certainly affected performance, but we had no idea what were optimal settings. So we were trying to set up a scenario where we could have some confidence that we were setting it to good values for our particular application. So our objectives were to investigate the background adaptation. Was there some way, in fact, we could take advantage of it to essentially pre-train speech profile to put out in cars and get better than out-of-the-box performance, so to speak. And also to study the engine parameters and see where they're given the analysis of our database of pre-recorded speech or of recorded speech out in the field, where there are good settings. And finally, to look at, as new engines came out, to look at comparing new engines against the 5.1 engine, which was our standard at the time. So again, our data we had available, we had 34 speakers. We had 7 from testing that went on, so they basically were employees of the lab, and 27 police officers in normal use. And for the purpose of this data that I'm going to show you, we basically filtered out all of the unrecognizable examples. Yep.
The same officer used the same car every time?
Yes. Because all of this data came from the state police. The local police tend to have the same cars on the road all the time, and each shift comes in and sits in the car. For the state police, in fact, people are assigned cars. So they have their own vehicle. Basically, for this, all the what we considered unrecognizable examples eliminated, and so that means phrases that weren't in any grammars were taken out because you can't possibly get that right if it's not in the grammar. Things that were so severely truncated by push-to-talk that a human have to really guess what was being said, and similar things that were so severely affected by audio interference that a human listener would have a hard time figuring out what was said. So we left in lots of examples with background interference and so forth, but the kind of test was, would it be reasonable to expect a human to understand this? And given that database that was left, the 5.1 out-of-the-box performance was 92.8 correct, 4.8 incorrect, and 2.4% unsure. Again, giving these were now all in grammar expressions. And so we divided that into test sets, a small test set of 500 examples and a larger test set of 10,000 examples. And the test set included, the small test set included about 137 different commands, the big test set about 376 different commands, but again, many more examples. So there was 454 examples of 137 commands and 9,000 examples of 376 commands in the big set. There were 46 alphanumeric strings in the small set and 723 alphanumeric strings in the big set. And those tend to be either license plates or spelling out people's names. And finally, on those test sets, the performance was 80% correct and 10% incorrect and 10% unsure. And you say, how did those numbers come out so perfect? Well, because the problem was we were worried that we wanted to tweak things and find improvements in performance, so we didn't want the database scores to be too good before we started tweaking because we were afraid we wouldn't recognize improvements when we saw them. So we tried to have the test sets have more challenging examples in them so we could try and tweak it to do a good job on the ones that it was failing on to begin with.
So one thing we noticed when we use alphanumeric examples is that there are more confusion, such as like 8 with 8. And do you have constraints in your license plates where you know that the first 2 items are letters and the last 6 are digits, or vice versa, that you could use? Or just put like a loop, any item can follow any other item in digit?
Now, unfortunately, for things like, for example, your driver's license number, not the vehicle plate number, but the driver's license number, those tend to have a format to them, so you can say, okay, it's 2 digits and 3 letters and 5 digits or whatever. But driver's license plates, other than saying there aren't going to be any more than 8 characters or something, because of the vanity plate thing, there are no rules. You can find anything, including punctuation, right? I mean, there's a set of punctuation you're allowed to have as well as numbers and letters, and you can't come up with any rule because as long as I'm willing to pay for it, I can get anything I want.
So did you look at using like Alpha Bravo kind of military stuff?
Yeah, in fact, I can actually show you later on at the end of the talk, I could show you some examples of that. So anyway, the test set was kind of deliberately tweaked to be a little harder than the real set, just so we could see improvements in performance. And the training set then was whatever was left. So the training set had about 44,000 examples, and it was running about 96% correct and 3.3% incorrect.
With the test sets and training sets and stuff like that, when you were transcribing everything, did you also annotate whether or not there were different kinds of noises in the background?
No. Okay. And there were noises. I could actually play some examples when we're done here. So then each thing is described by a control file, and the control file has the obvious stuff: the name of the WAV file that contains that speech example, the transcription of what it was. In this case, someone said code 1. And then finally, the name of the grammar. And this grammar is the normal Project54 grammar that contains that command. And again, Project54, it's a bunch of different screens to do different things, like a screen to control your radio or to your light bar. And there are screens that have mix and match. But each screen has its own grammar set. Right, so if you're in a screen that's controlling your video system, you can't activate your front radar antenna because you're not in the screen that does radar. So you're switching grammars, and the grammars tend to be anywhere from 20 to 60 commands in a grammar. So there's a large total command set given all screens, but at any given time you have somewhere between, say, 20 and 60 commands you can give depending on how the level of complexity. And so the third thing is which Project54 grammar to put in place that has that command. And a basic assumption, look at this, with the background adaptation is that, again, you have to remember that our view of the speech recognizer is it's a black box with a SAPI interface. I mean, we have no way of knowing what's happening inside. We only know what we can see from what we can touch with SAPI. And what we could see with SAPI is we could turn on background adaptation, but we could never reward the recognizer or punish it. We could never tell it was right or wrong. So if it was doing background adaptation without us ever saying what the right answer was, then obviously it seemed to be doing some sort of unsupervised learning or decision-directed adaptation, that it was assuming that it was right and taking its own classification as having been the right answer and then tweaking things based on that. And we said, okay, if that's the case, then one possible way of doing supervised training would be to create a grammar that has only the correct phrase in it, and activate the grammar that has only the correct phrase, and then play it the audio, and then if it has to either classify it as correct or be unsure, and thus it's not going to adapt incorrectly. So that was our strategy for training.
That's basically what the training wizard initiative in the OS did.
So our testing procedure then is to put in the real Project54 grammar that contains that phrase, and then feed in the audio and compare the right answer. So that makes sense. So when we're training, we're putting in these one-word or one-phrase grammars. When we're testing, we're using the normal grammars we would use in the field. And in training, we basically, it's getting random exposure. We just choose examples at random out of the test set. That's the major thing. And in testing, in the data I'm going to show is the scores will be based on one sweep through all of the 500 testing examples. And then what we did is verify the major trends and results against the big test set. The problem is it takes, to go through the small test set takes about 17 minutes. To go through the big test set takes about 5.5 hours. So if you want to see the performance as a function of training at lots of different points, if you had to do 5.5 hours of evaluation at each data point, it would take weeks of time to actually do it. So basically what we tended to do was do evaluations with the small set and then verify our conclusions by running the big sets at those particular settings.
So you weren't doing speaker independent, you're only doing, you're building a speaker independent model?
This is speaker independent, that's correct. There's no, in other words, it's the testing sets were chosen randomly from our big data set, and then the training was, again, whatever was left in the data set. So there's examples of all speakers in it. And basically the two recognizers that I'll talk about today, one is the 5.1 recognizer that ships with the speech SDK version 5.1, and the other one is the 6.1 recognizer, which we originally got from the speech application SDK. I think also ships with Office 2003. You would know better than, but I think that's correct.
You can call up PSS and they'll give you just that on a CD as well.
Oh. So this shows an example of the performance. Now this is, most of the results I will show are with the 5.1 engine, unless you see otherwise specifically, and that's what we actually utilize in the field. What we have here is this is number of training examples out to about 20,000, and this is a performance score, and the performance score is the number right minus the number wrong divided by the total, because basically when it's testing, it's always saying in grammar phrases, right? They're never out of grammar. And in that situation, wrong is worse than saying unsure, because when you do something, when you come up with the wrong result, you take a wrong action. Whereas when you say unsure, then you have to repeat the command, but that's a better thing. So basically, we give it a point for being right, we take away a point for being wrong, and we divide by the total. So a negative score would mean you're wrong more than you're right. And again, remember that the 0.7 score is artificial in the sense that we tweaked it to be 80% right and 10% wrong, so 80 minus 10 gives 70 divided by 100. So that's our out-of-the-box starting point, And then, again, this is a function of training. And each dot along here, we would do a training phase, which would be about 900. Because they're being selected at random, there would be about 900 training examples, and then we'd test on all 500 testing, and then we'd do 900 more training and test on 500. These three curves are with three different training procedures. The blue curve is the one I suggested, which is make a grammar that has only the correct answer in it, and thus it has to be right. The green curve says put the normal Project54 grammar in place that contains that command. So now it has the possibility of being wrong, right? But in fact, it's got the right answer is in the grammar. But it's more like having adaptation turned on while you're out in the field, in a sense. However, what the red is we took a fixed grammar that had some of the commands but not all of the commands in it, and put that in place during training so that most of the examples that we're hearing were out of grammar, just to see what would happen with adaptation when it's hearing out of grammar examples and thus likely to give wrong. And of course what happens is you get the best performance when it has to be right. But again, remember, in testing, in all of these cases, during testing, it's using the normal Project54 grammar. So there's no difference between testing one of these and testing up here in terms of what grammars were used. It's the grammars used during training. But clearly, the profile got adjusted the best when it was using the single phrase grammars. It improved in performance, but not as much when it was using the normal Project54 grammars. And in fact, when we used a fixed grammar so that there were a lot of out of grammar examples, the profile, the performance got much worse.
So you extracted all the unintelligible noise from the training set before you ran as well?
Yes. We didn't extract all the noise. There are plenty of noisy examples, but they were all such that I could listen to it and say what was being said. This is an example of, okay, this is that same blue curve from before, so this is kind of the best case where you train with it. And this red is the same as before, was training with the ones with the out of grammars. Then it said, okay, let's take this profile and put it in place, and then start training it with the single phrase grammars to see once a profile's kind of messed up, can it recover if it starts hearing good examples in grammar kind of things. And the answer is, well, it's weird. Because you see it took about 5,000, again this is 70,000 training examples out here. It took about 5,000 training examples and the performance level stayed really bad, even though during these it's hearing audio with only the right phrase in the grammar.
So the engine only adapts periodically, and it adapts something like, each time it adapts, it needs 1.1 times the amount of audio it had last time.
Okay.
So by the time you've gotten up to whatever that is in the red, 20,000 examples, it's not going to adapt very frequently, and so that's why you see it.
Okay, that's why there's big jumps.
Right. Then you can see again. There's another big jump after
Yeah.
Well,
and that's exactly the kind. I mean, again, that's all mystery to us because we've got a black box we can touch. But this explains exactly why we were seeing that when a car would come in with a really badly adapted profile because it had been turned on, and the bad adaptation was probably the result of out of grammar kind of things as the officer got used to using the system. That the only way to recover it, because here, for example, it took 5,000 examples before anything happened, and that would take forever if in actual use to give 5,000 commands to your car would take an awfully long time. So basically we were seeing it get stuck, and that phenomenon is exactly what we were seeing. So the final conclusion to that was, in fact, the background adaptation can significantly improve the performance in the way we did it based on the training set if the classifications are correct, and it could significantly degrade performance if you're doing out of grammar stuff. So the best thing to do was to pre-train profiles on our training set and then turn off continuous adaptation, which is exactly what we do.
But you never did the speaker dependent.
No, that's correct.
Is there a reason you chose the speaker independent route?
Because, in fact, again, an awful lot of cases, there are multiple officers in a shift, and who knows what's going to get what car, right? So you really want to be speaker independent. And even for the state police, while they get assigned a car, quite often their car's in the shop and they've got to use another car and so forth. And so the speaker independent is a much preferable model if possible. And again, the training cut down the errors, if you look at those numbers, it really, from the out-of-box performance to our after-training kind of thing, it cut down the number of errors by about half. About half of the unsures became correct classifications, and about half of the misclassifications became correct classifications. So it's a significant change. I mean, enough so that when we put the trained profiles out in the field, people started saying, geez, what did you do? This works better. Another question was the threshold. Is there something we could do with that recognition threshold? Because an issue is what happens when you have out-of-grammar examples. You would really like, rather than taking the wrong action, you would like to say that it didn't understand. And so what we did, this is after training now, so, or actually this is both. This is the red line here is from the out-of-the-box profile, and the blue line is our pre-trained profile. But we're just doing the speech recognition threshold, sweeping it from 0 to 100. The top two lines, we're doing the recognition with the correct Project 54 grammar during the test. All right, so the profile is fixed. We're doing the test with the correct grammar, so it's always an in-grammar phrase. In the bottom two lines, again, we take a fixed grammar that contains some but not all of the commands, so many of the phrases are out of grammar. So it can't get them all right because, in fact, many of the phrases aren't in the grammar, so it can't possibly get them right. But you wish it would say unrecognized or whatever in those cases. All right? And then we sweep the threshold. And up here is what you'd expect, is that you have fairly good, essentially constant performance until you get to a knee of around 70, and then it starts falling off because, in fact, it's starting to say unrecognized when, in fact, if you'd put the threshold lower, you'd get a correct classification. So that's fine. But down here, it's actually getting a negative score because it's getting lots of them wrong, right? Because they're out of grammar and rather than being unrecognized. And you're looking for where does the score actually start improving because it starts turning wrong classifications into unrecognized. And you're hoping that there's some knee there where the score will start to improve, and there is. And so the score is getting better here as you crank up the threshold because you're filtering out a lot of those misclassifications and turning them into unrecognized. So you're taking away the -1s and making them a 0. And so what you'd like to do is set the threshold somewhere above this knee, so you're getting advantage of this, but below this knee, so you're not falling into here, and unfortunately that doesn't exist. In other words, the only way to start rejecting the out-of-grammar phrases is to lower your score on the in-grammar phrases, and that's the paradox that we're in. And so we intend, we put them out in the field with a threshold of around 70, which means basically we opted for being right if you say something in grammar, and you're on your own if you say something out of grammar.
So do you have any statistics about how much of the utterances were out of grammar?
Yeah, and that was in what he was talking about. And it's a fairly large number, although we're collecting a lot more data now, and it'll be interesting to see because we have a lot more experienced users. Our original data set was more novice users because now we have people that have had the system for 3 years and things. So an interesting thing would be to see what's happened with out of grammar now that, in fact, many of the users are pros as opposed to being new.
So how out of grammar are these phrases? Are they partial matches to something that exists in the grammar, or are they completely,
it's totally possible.
I said, turn the radar on and like...
anything, because what it is that it occasionally is something that's not in any grammar, but that's unusual. The more common thing is you're in the application to control the radio and you forget that, and you say something like front strobes to turn your front strobes on, but there aren't any front strobes because you're in the radio application.
So often the thing that is out of grammar is completely different from...
Right, except that you might say you might be in the application to control your radio, and there's a front antenna command to activate the front radar antenna, and you say front strobes. Now the word front is in both grammars, right? In one case it's the front radar antenna, in the other case it's the front strobe. So it could be kind of half things too.
So in your scenario, does it make sense at all to have any kind of sort of dialogue repair as opposed to, so it seems like what you're doing is you're setting a threshold and anything above it is sort of accepted as is, anything below it is more or less rejected. There's no sort of, did you say something, right? Like there's no yes/no confirmation, there's no partial recognition, like, I heard this radio station, did you want to turn it on or turn it, set it to memory or things like that. Like, does it make any sense, I guess, for police officers in these scenarios to have any kind of...
yes, I think you could do that, where, again, assuming, the frustrating part of that would be if you said something very clearly and there wasn't background interference and the system came back to you and said, did you say front strobes? And you obviously said front strobes and there was no interference and everything. In other words, if the uncertainty measure was coming out in favor of uncertain, even though it was really clearly spoken, that would become a frustrating thing for them, right? I mean, I think people realize that if they say the wrong thing, they would like it to say, sorry, I don't have any idea what you're talking about. Also, if they said something and there was a lot of background noise or something, I think people would understand if it said asked for a verification. The problem that we've had in doing that is really, I'm not sure that in looking at the confidence thresholds that come back from the SAPI interface that you can really set that threshold that they're that meaningful in that kind of a way to do that dialogue. Now, again, we haven't looked at the most recent engine, but I'm just not looking at the 5.1 doesn't really return. I mean, it returns 1 all the time. The 6 engine returns a number, but it's not clear that that number is valuable enough to use. And again, we don't have access to any internal measures. We just have what comes out.
We've done some work to improve the confidence score, but I don't think it's in the latest build yet. Right? But so
hopefully it will be. I'm sure confidence has improved since the 5.1 engine, but yeah.
But the work that we did over the summer reduced the. Yeah, it's not there, but it's a factor of 3 better.
So basically, we put it out now with a threshold of 70, and it's on its own. And that's good because the problem is, the most frustrating thing is when you say the right thing, while in a way it's bad if you say the wrong thing and it does the wrong action. In fact, the most frustrating thing for users is when you clearly say the right thing in the right situation and it doesn't recognize it. So we opt towards a setting which, if you say the right thing in the right situation, is likely to get it right. And they just have to deal with it if it does the wrong thing when they say the wrong thing.
Could you help us understand what you say to get from screen to screen? Like if you're in screen 1 and you want to say a command that's in screen 2, what does an officer, does he say?
Yeah, actually, I can actually bring up the app in a minute if you want and see that. But you'd say like radio controls or radar or whatever to switch to a particular kind of device.
So all the screens are in each grammar. Each grammar contains a list of all screens.
No, what happens is they're kind of the most commonly used screens are in all of the grammars.
Okay.
And then there's what we call the main screen that you go to that has a lot of utility things that you might want to switch to. But if you kind of want to go to the second tier screens, you go to the main screen, which is really just a big list of other things you can do. Okay. But the most common screens link to each other so you can get directly from one to the other, essentially.
Have you done any experiments, like in the scenario where someone says a command that's on a different screen, where you would back off to like a global grammar that has all the commands and see if you're able to get recognition?
No, we have not done that.
Can you talk about, at some point, how big your grammar is? Like the all screen, how many screens, and the grammar in each screen? Like is it 1,000 utterances or 2,000?
Probably more like 1,000.
Okay. Over 100 screens or something?
Yeah.
Okay.
Well, no, not over 100 screens. No, maybe 25 or 50 screens. I mean, maybe 30 screens, I guess, or 40 screens. Okay. It really depends on the police car because it depends on what equipment's installed in it. Right, because a lot of it's customized, and it depends on their data query capabilities. Some people really just have basic motor vehicle queries, and other cars they can run criminal records checks and all kinds of things, and so they have screens for doing those kinds of things. So it depends on kind of the capabilities that have been built into it. Okay. So this is one where I think that hopefully we can get some good feedback. And that is that we tried switching to the version 6 engine, which was again that we had, and found very disappointing results essentially. I mean, dramatically worse results in our situation. The out-of-the-box score went from, on the same data, went from a 0.7, which again was pre-tweaked to be 0.7, with the 5.1 engine down to about 0.5. And we did the same kind of training procedure, and it got up to about 0.7 with that same kind of a training procedure.
There are a couple big differences that you may be hitting. The 5.1 engine includes support for both 8 kHz audio and 16 kHz audio. And the 6.1 engine only supports 16 kHz audio. So if you're using 8 kHz audio input, then I would probably expect it to be a little worse than this, though. The other thing is the 5.1 engine was more a generic speech recognition system, and the 6.1 engine was more targeted for desktop use.
Right. And so that may be the thing, but that's exactly the kind of feedback. And again, all we see is the SAPI interface, and we plug in the new engine. But clearly, we didn't get the same kind of performance out of it in our scenario, and we tried thinking maybe it was a threshold setting kind of thing, but we've experimented a lot with thresholds, and it seemed like with the recognition threshold had relatively modest effect on this. Now breaks it up into separate scores of right. These are right divided by total, and these are wrong divided by total for the 5.1 engine and the 6.1 engine. And again, the 5.1 engine tends to do what you do. The number right drops off dramatically as you get a threshold near 100, and the number wrong goes to 0 as you get a threshold near 100. Whereas it seems like the 6.1 engine, those hardly changed at all as you swept those parameters. And so again, we ship the 5.1 engine is what we install in cars, and for those reasons. So what are kind of the final conclusions of this? Well, basically, the supervised training technique made a significant improvement, and that's what we ship. We ship a pre-trained profile with adaptation turned off, and that's our what we ship with the 5.1 engine. We set the threshold at 70 to just try and get as many right as possible. I mean, we could easily set it at 0 because you'd get essentially the same behavior. The qualitative evaluation of how it works is this, that in fact it's extremely strong in grammar phrase recognition, even in background noise. That it does occasionally make a mistake, but if we could improve that performance on in-grammar phrase responses, people would hardly notice. In other words, if we could prove that performance statistically, it's so good that in fact no one would say, geez, this is suddenly working really much better. In other words, in-grammar phrase performance is essentially good enough. You always would like to get rid of any remaining errors, but the fact is it wouldn't make much difference. It's less strong on alphanumeric string responses because of the obviously they're less structured, and there's a lot more ambiguities that you can run into and so forth. They do alphanumeric strings by saying, A Adam and B Boston or B Bravo or whatever. Different police agencies use different things. But even still, the alphanumeric strings, it's more likely to make mistakes. It's good enough that people want to use it. They do use it and want to use it, but it makes enough errors that they wish it made fewer errors. Right? So it's not so bad that people just give up in frustration and don't use it. But in fact, there are enough errors that people would certainly notice if that error rate went down.
So 80% was at the letter level or at the string level? Letter or number?
Is it the entire phrase, or is it
string?
Getting the entire phrase wrong, or getting one of the words? Is it word error rate or
string?
This is getting. I don't know what the 80% is, but I'm just.
Where you started, right? Where the 80, 10, 10. So all the errors are anything wrong in the phrase.
Right. That's right. That's correct.
So you make one mistake in the alphanumeric string, you consider that entire phrase.
Right, because you're going to run the wrong license plate, or you spelled the person's last name wrong, or whatever. So you got to, you know, unless you have a bunch of voice editing commands, which becomes, I mean, the easiest thing to do is just to re-enter the whole string again.
It was just to clarify whether it was word array versus string sequence.
Right, but that's what it is. And I mean, that's the problem also, is you got multiple digits, so you're compounding your statistics, you know, your chances of making an error. But just from the standpoint of what could be better, you know, again, recognizing individual commands could hardly be better. I mean, it could be a little better, but hardly anyone in the user community would notice. Alphanumeric strings could be better, and people would notice. But, you know, it's good enough to use, but it's not perfect. On the other hand, out-of-grammar phrase response is, you know, you ideally would like it to say you know, that it's out of grammar or that it's unrecognized or whatever. And in generally, for the, you know, the majority of the cases, it says it matches it to something totally different.
So the out-of-grammar utterances for, or not out-of-grammar, but rather the misrecognitions for alphanumeric strings, do you have any sense of how many of those are maybe the wrong number of characters as opposed to getting an individual character correct?
No, you get both, and I don't have any statistics on that. I mean, you see misrecognition of characters, but you also certainly one common thing is background noise will add a character. In other words, it'll be doing an alphanumeric string, and there'll be an extra number at the end, which actually, when you listen to the audio, was a background noise. But you'll also see alphanumeric strings that were quite clear, it seems like, and yet it will make a mistake.
Have you considered a dynamic grammar where you prefix with the number of characters that will be coming? So, for instance, you know, you say the button say 7, and then it comes back and asks you to.
No, we have not done that. That's an interesting idea. But again, that's kind of you know, the two things we would like to improve are those latter two things. Anything in those directions would be great. And then finally, the 5.1 engine certainly is much better suited in our application, at least, than the available 6-point engine.
I mean, you may be able to say, you know, this is the vanity plane versus you know, regular stage data, and it's assumed that the regular stage data has more constrained length or a clearer, you know, fixed length to them.
I mean, there is some variation in all the license plates. There's actually some pattern to them. They don't allow every letter combination and every number combination to show up because they don't want. There's some you know, quote unquote error correction built into the system because you know, so you know, there's only a certain number of certain types of letter combinations that are allowed to avoid, you know, confusions. To some degree, but it's difficult because you'd have to have access to the database of all the valid license plates.
Right.
It's kind of hard to come by.
They vary for safety states, and they vary from like whether it's a car, truck.
Yeah, and then there's like old, one of those collectible card kind of license plates versus old license plates.
You could specify the license plate type. You're right, and then if you had the statistics for.
I could play a few strings if you'd like to just hear what it. So these are a few audio examples of.
And Nora E. Edward R. Robert I. Ida.
And Nora E. Edward R. Robert I. Ida.
So during this pause, it's actually saying it to the SAPI engine right now. So the response you're hearing is the SAPI's response.
K. King, I. Ida, E. Edward, R. Robert, A. Adam, and Nora.
K. King, I. Ida, E. Edward, R. Robert, A. Adam, and Nora.
So do you always have them use like military?
R. Robert, E. Edward, D. David, I. Ida, and Nora, G. George, D. Tom, O. Ocean, and Nora.
E. Edward, D. David, I. Ida, and Nora, G. George, D. Tom, O. Ocean, and Nora.
It missed the R there, but other than that, it was correct. But.
C. Charles, O. Ocean, U. Union, R. Robert, C. Charles, Y. Young.
C. Charlie, O. Ocean, U. Union, R. Robert, C. Charlie, Y. Young.
And just some example you might want to hear.
B. Boston, E. Edwards, C. Charlie, K. King, O. Ocean, W. Walter, I. Ida, T. Teton Z Zebra.
That was the last
Boston
alphanumeric.
Edward C. Charlie K. Kilo Ocean W. Walter I. Ida T. Tom Z. Zebra.
I might need to restart this, yeah.
M. Mary A. Adam R. Robert K. King.
And Mary Day and R. Robert K. King.
Try this. Oh, let's go.
Siren off.
Siren off.
Siren off.
Siren off.
Siren off.
Siren off.
No, it works.
Siren off.
The interesting
Siren
thing is that, in fact, non-speech noises, the 5.1 engine is
Siren
very
off.
resistant to non-speech noises. I mean, it works quite well. It's talking on the radio,
Siren
which is
off.
the worst background noise is speech, not surprisingly. And it's talking on the radio
Siren
is the worst
off.
problem. So it does get some of these wrong, these examples of turning the siren off, but
Siren off.
in fact, it does quite well.
Siren off.
Siren off.
So the signal that you're recording.
Siren off.
Siren off.
Real quick, the signal that you're recording there, is that 16 kilohertz data, or what kind of, what kind of input signal do you have, and is there any kind of processing you do on it?
Oh, the wave data is 11025.
Okay. And are you doing any kind of processing of the audio, or it just goes straight what you get from the microphone? You were saying it's directional, so do you get like?
Well, yes, it's a 4-element. It's an Andrea. I don't know if you're familiar with those, but there's a thing, the Andrea auto array. So it's a 4-element with its own DSP that's doing its own beamforming.
Okay. Try the 6.1 engine with the 16 kilohertz audio.
Okay.
Okay, we still have some time for questions, but I just wanted to have the audience just thank our speakers for coming, and there'll be opportunities, by the way, for people to meet with them, and I know that they're interested in, obviously improving their speech interface, and whatever we can do to help their project will actually help police officers, so that would be good. Okay, let's give our speakers a round of applause.